Good morning, good afternoon, good evening, everybody. Depending on what time zone on the planet you're in, it's about noon here in Winchester, Massachusetts, and it's my great pleasure to get to hang out with you for an hour and answer all the awesome questions that you've sent me. So let's dig right in here. Let's begin with a video question that I got from April. Here is what April has to say.
Hi, Professor Max Tegmark. This is April from West Harrison, New York. My question pertains to the tiny speck of doubling substance which drove inflation and created the Big Bang, which created our universe. What do physicists think that this substance was? Could it have been negative matter? Since energy and mass are interchangeable, E equals mc squared, and anti-gravity most likely caused the universe to inflate, could this tiny blob have been negative matter?
So thank you, April, for this this excellent question. So just to repeat it, the question is, we believe that our universe was created by inflation. At least that's the most popular theory we have for what put the bang into our Big Bang. In which case there was some kind of substance early on, right, which was very, very hard to dilute, and this kept doubling and doubling and doubling its size over and over again, at least 80 times, producing more mass than everything we see around us in the world today. And your question, April, is what was that stuff? What could it have been? Clearly, it's not some sort of ordinary substance that we have around today, like cheese or protons or whatever. The simplest candidate for such a substance is a cousin of the magnetic field, something called a scalar field. Whereas the magnetic field is something which exists everywhere in space and has a direction and a strength, a direction that you can measure with the needle of a compass. The scalar field is something which has no direction, just a strength. So you can think of a scalar field as there just being a number sitting everywhere in space. A little bit like the temperature field is a number sitting everywhere in space, except that the scalar field has this different property that if it exists, and if that number is about the same everywhere in our universe, it's going to actually have this weird property that it just keeps doubling its size without hardly diluting at all. And another beautiful thing about this scalar field substance is that you can prove that after a while it will actually decay away, a little bit like a radioactive substance. And what it will leave behind then are the kind of particles, quarks, electrons, and photons that make up our universe today. We don't know for sure that the scalar field is what caused inflation or even whether inflation happened, but it's the Occam's razor simplest candidates for something that would work. Let's move on to some written questions here. So let us begin with a question from Michael, who asks, there's been speculation that the Milky Way is destined to collide with the Andromeda Galaxy in about 4 billion years. How can this be possible if our universe just keeps expanding? So the answer to this question, Michael, is that even though our universe as a whole is expanding, which means that really, really distant galaxies are all flying away from us, not everything is expanding. Earth is not expanding, our solar system is not expanding, our galaxy is not expanding, and because these things are all held together by gravity. And even nearby galaxies like the Andromeda Galaxy, that's not expanding away from us. The Andromeda Galaxy is actually coming towards us. And that's why it's going to crash into us about 3.5 billion years from now. So the picture you should have is on large scales, things are just uniformly all flying apart. But on smaller scales, the expansion has stopped, and in some cases, things are even crashing together. Finally, I wouldn't get too freaked out or worried about Andromeda colliding with us in 3.5 billion years, because first of all, it's not going to be necessarily a total disaster. Most of the stars in the two galaxies are going to miss each other, and it's going to more be like a giant merger into what we might end up calling the Milkomeda galaxy. Although it's going to be pretty spectacular, triggering a lot of other crazy things to happen, we have other things to worry about on a much shorter time scale. Our own sun, for example, is going to gradually keep getting hotter, and 1 million years from now, it'll cause all the oceans to evaporate. That we can fix. We can use asteroids to very cleverly nudge with our gravitational pull Earth into a wider orbit, so we can survive the death of these problems with the sun. As long as it takes a few hundred million years to do it, but we'll be fine as long as we start with this project, within 100 million years. What we should worry much more about are all the stupid, short-sighted things we humans do ourselves. I think if we can get our act together and not self-destruct, then we're in a good position to deal with the death of our sun and the Andromeda collision when that time comes. Let's take another video question now. Let's take a look at the question here from Elliot.
Hi, Professor Tegmark. My name is Elliot. My question is about how gravity relates to quantum decoherence. So I'm wondering, since gravity is nonlinear and it has its own interactions built into it, even if there's nothing else interacting, do you think there could be circumstances where the gravitational field could, so to speak, measure itself through its own interactions and decohere itself so that the outcome is a classical space-time? Thank you.
So thank you, Elliot, for asking about gravity and decoherence and why space-time seems classical. So just so we're all on the same page here, this has to do with quantum mechanics, where we know that everything that can be in one way can also be in more than one way at the same time. We're familiar with this happening with particles, an electron being here and there at once. But if gravity itself also obeys quantum mechanics, that means that even things to do with gravity, like the nature of space itself, can be in two different ways. So, for example, the distance between me and my webcam should be able to be 1 meter and 20 centimeters at the same time. Whoa, that seems really different from what we actually experience. That space seems to be this very well-defined thing where the distances are what they are and space always has these classical properties. So quantum decoherence is a mechanism that you can derive from simply solving the Schrödinger equation of quantum mechanics, which provides a kind of censorship effect. And then what it explains is how even if a lot of quantum weirdness is going on, you will usually not observe that weirdness. So even if a particle is here and there, quantum decoherence says that if some other system finds out, if something else finds out where the particle is, then the secret is out. And quantum superpositions only work when they're secret. So now it's going to seem to anyone who looks like the particle's either there or there. And the excellent question you're asking here is whether something can find out whether space is in this way or that way, so that for all practical purposes, anyone is going to see space only being in one particular way. You're quite right that because the laws of the equations that govern space itself, namely general relativity, are what we call nonlinear. It means that space can, in some sense, observe itself. For example, if the space here between my hands has both the radius of the diameter of 10 centimeters and of 20 centimeters, then if you have a graviton, which is just a ripple in the space itself, or a gravitational wave that flies through here, afterwards, this gravitational wave will be in two different places depending on what the space was doing. So now this gravitational wave, in a sense, knows what the distance was it had to travel. And anyone looking here later will find it in only in one way or the other. So this warping of space, the gravitational wave, effectively made the rest of space kind of classical. In fact, together with a student, I worked this out mathematically in a paper a while back that we're just writing up now, and found that this is exactly what actually happens. There are all these disturbances that fly through all the time and keep checking out how space is behaving. So space can't really keep many secrets about how wide it is and its geometry, and that makes it very classical. We found actually that the most effective cause of space seeming so ordinary and non-weird is not space measuring itself with gravitational waves and such, but actually other kinds of particles flying through. For example, and in particular, there are these neutrinos, these ghost-like particles from the early universe that are everywhere, that were created shortly after our Big Bang. Even they fly through everything. We can't keep them out. And by doing so, from all different directions, much like X-rays fly through your brain in all directions if you're doing a CAT scan, enabling you to reconstruct in 3D what your brain looks like, these neutrinos keep flying through all parts of space at the same time, much like a CAT scan, and figure out always what space is doing. There is no secrecy in the geometry of space, really, which helps explain why it looks so classical. So decoherence very much works and helps us understand why space itself so far hasn't revealed much quantum weirdness to us. Let's take a written question again. This time, let's take a question here from, let's see. From May Rose, who wants to know, how do virtual particles work? And how do they not violate conservation laws? So what's a virtual particle? Well, a virtual particle, what we're talking about here is that in space, in physics, it turns out nature just hates a vacuum. You try to make a vacuum, you try to take out all the air particles from here, from this region of space. You try to take out all the photons, all the light, try to make it completely empty. And you'll find that what happens is, nonetheless, some particles just suddenly just pop into existence very briefly and say, hello, and then they disappear again. In particular, what might happen is you might get an electron and an anti-electron, a so-called positron, just popping out of nowhere and saying, hi, and then, oops, we're not allowed to be here because we violate energy conservation, and then they disappear again. How can they do that? Well, it does violate energy conservation, classically, but there's a loophole in quantum mechanics. There's a quantum uncertainty relationship that says that the uncertainty in energy, there's allowed to be a little bit of uncertainty in how much energy there is, as long as it doesn't last for very long. As long as it doesn't last for more than Planck's constant divided by the energy you made. So the more energy you create that's not supposed to be there, the shorter time it's allowed to live. So what happens is these virtual particles, they tend to, especially if they're heavy, they appear just for a very short time and then they pop out of existence again. This might sound totally crazy, but this has been observed again and again in many physics experiments, that these virtual particles are actually there. And in fact, that's one of the ways of understanding how black holes can evaporate, like Stephen Hawking famously showed. Virtual particles get created, and then one in the pair gets eaten up by the black hole, and when the other one tries to annihilate again with it, it can't, because the other guy's gone, and it's like, okay, I guess I have to go on existing then. Let's come back. Let's to the next question here. Then we have a question from Ritajit, who asks, you explained how we can observe stars 30 billion light years away, even though our universe is only around 14 billion years old. So our universe, again, is this spherical region of space here, from which light has had time to reach us so far during the 14 billion years since our Big Bang. Okay, so he's wondering, how can we see stuff which is 30 billion light years away? He says, you said that we see the star as it was many years ago, not in its present state. But using the same argument, shouldn't the entire universe be observable as it was many years ago? So here's the answer. Stuff at the very edge of our universe, we see the way it was 13.8 billion years ago, because that's how long it's taken light to go from here at the edge to us in the center. Stuff which is very close to us in the center, say if 1,000 light years away, like some star you might see at night, that light has only taken 1,000 years to reach us. So we see that the way it was 1,000 years ago. So the nearby things we see pretty recently, the farther away they are, we see them the way that they were really, really long ago. Things which are even farther away than this, we don't see at all, because light from there just hasn't had time to reach us yet. Let's do another video question. This is a question from M. Coriel. You look pretty comfortable there in your sofa.
Professor Tegmark, my name is Mitch from Washington, D.C. In your book, Our Mathematical Universe, you describe the smallest fundamental particle of matter as being a one-dimensional point with quantum mechanical attributes. I understand your premise, however, what I don't understand is what that one-dimensional point of matter could be made of. Is it strings? If it's not string, what else could it be? It must be made of something in order to make up a macroscopic object such as myself, a star, or a planet. Please explain what you think matter at its most fundamental level is really made of. Thank you.
That's a great question. One of my favorite things to think about, in fact. What is everything ultimately made out of? I'm made out of molecules. They're made out of atoms, which are made out of electrons and protons and neutrons. The protons and neutrons are made out of quarks, etc. Well, but what are these particles themselves ultimately made out of? What sort of properties do these particles have? Well, we tend to take for granted that ultimately everything is made out of some kind of stuff, right? And stuff must always be made out of smaller stuff. But the strange thing is that the smaller the building blocks we zoom down to, the less stuff-like they actually appear. If you look at a big thing like me, or you might say, well, okay, I'm brown-haired, I'm a little bit crazy, or I have a funny accent, whatever. These don't sound particularly like mathematical properties. They sound like the properties that a person might have. That, if you look at stuff, you might say, well, this stuff here is gray, this stuff here is soft, my teeth are hard. But what properties do my building blocks have? My electrons that I'm made out of, for example, what properties do an electron have? -1, 1/2, and 1, and so on. We physicists have geeky names for these properties. We call them the electric charge, the spin, and the lepton number, but the electron doesn't care what we call them. They're just numbers, just mathematical properties. And the interesting thing is, I write a lot about this in chapter 7 of my book, Our Mathematical Universe, which is what I based these lectures on. So if you're interested in drilling deeper in any of these topics we're talking about now, I hope you'll find this book useful. And for your question, in chapter 7 here, let me just show you, see if you can see it, a little table I made with the properties of the electron and all the other most common particles. Don't worry about the details. Just note that the only properties that are listed there are a bunch of numbers. And the only difference between an electron and an up quark and a photon, are the numbers that are their properties are different numbers. So it seems like, to me, it seems like ultimately these particles are mathematical objects in the sense that they don't seem to have any properties at all except mathematical properties. Now, some of my physics colleagues have said that, or philosophy colleagues rather, have said that, well, maybe particles still have one more property that isn't mathematical, namely physical existence. But even that actually doesn't really seem... That seems to be pretty undercut by what we've discovered in quantum field theory, because before, in the old days, we used to think of an electron as a thing, like a little bowling ball or whatever, except smaller and simpler. But in quantum field theory, the electron isn't the fundamental thing. The fundamental thing is what's called the electron-positron field. It's a quantum field. And similarly, the photon isn't fundamental. There is something called the electromagnetic field. What's the electromagnetic field? Well, it's a mathematical thing obeying certain equations, and it basically has a bunch of little counters you can turn, click, 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 kind of like the dials on a combination lock, which say how many photons there are of different frequencies and stuff. So if this is set to 0, then there's no photons. If you turn the knob in the field to say 1, that means there's 1 photon. If it says 3, there are 3 photons. So then what properties does the photon have? Really, nothing. The photon, the number of photons is itself just a number to do with this field. And right now, I think we can't say for sure that I don't think we have any indication at all that any of the stuff in our universe has any properties at all except mathematical properties. What about the space itself that all the particles are in? What properties does space have? It has the property 3, for example. That's the largest number of fingers I can hold. 1, 2, 3, so that they're all perpendicular to one another. We, again, have a geeky name for this in physics. We call it the dimensionality of space, the number of dimensions of space, but it's just a number. And Einstein came along and discovered space has some more properties too, called curvature and topology, that are also purely mathematical. And so far, we actually haven't discovered any properties at all of neither space nor the stuff in space, which aren't purely mathematical. So this idea, when you first hear this idea that I explore in the book, that somehow nature seems to be deeply mathematical, it sounds kind of cuckoo. But if you take seriously the idea that we haven't discovered any fundamental properties of anything that aren't mathematical properties, it sounds a little bit less nutty. And I think it's a very real possibility that ultimately the answer to your question of what the basic building blocks are of stuff is the basic building blocks of everything ultimately is mathematics. It's all mathematical. We're part of this beautiful mathematical object. Let's take a question now from Peter. Peter wants to know, we appear to be at the center of the visible universe, the center of this, because it's where we're looking from. But how does our view compare with that of someone near the periphery of our visible universe, like here? And how does that inform the spatial geometry of inflation? So first things first, how does our view of our universe compare with someone who is here? Excellent question. Someone who lives here, now, they will be able to see all the light that has had time to reach them since our Big Bang, 13.8 billion years ago. So they'll be able to see stuff that's over here, where light has taken 13.8 billion years to get to us, and here. They will be surrounded, if you draw a sphere around them, exactly the same size. If you draw a sphere around this guy, exactly the same size as this sphere, that's what they're going to call their universe. And the place where we are in will be exactly at the edge of their universe, except they're not going to see us now having this live cast and talking about cosmology, because they're going to see the region where Earth is the way it was 13.8 billion years ago, before Earth had even formed. In other words, we shouldn't think of our universe as this fixed mad thing that has like its own existence independent of us humans. This edge here is not the edge of anything physical. No, there's nothing special there. This is just the edge of what we can see. Space continues contiguously way beyond this. Much like if you walk around on a really foggy day where the visibility is only 100 meters, you will feel that you are in the middle of a fog sphere of radius 100 meters. You can't see anybody who's more than 100 meters away. But if you went up to the edge of that fog sphere, you wouldn't see that that's the edge of our universe, the edge of reality, the edge of space. You would find that there's nothing special going on there. And in fact, when you're there, you would again feel that you're in the middle of a 100-meter size fog sphere. If you go back to the center of where you were standing before, you could maybe see some guy standing right at the edge of your fog sphere, and you would know that he would be able to see things that you cannot see farther away. So the whole level 1 multiverse that I talk about in the 6th chapter here, you could just as well call it just space. Our universe is just a small part of that space, the part that we can see. And anyone else really, really far away will call the part of space they can see their universe. This is why I want to be kind of modest to keep say our universe instead of the universe. Because I think talking about the universe is kind of arrogant. It sort of suggests that the part of space that we can see is the only part that exists. Much like an ostrich with its head in the sand like this, saying, oh, if I can't see stuff, no, it can't be real. How does that inform the spatial geometry of inflation? Well, basically, what we've seen in our universe, the fact that space seems so flat and that space has all these properties and that the colored blobs at the edge of our universe have the properties they do, agrees beautifully with the inflation model. So that makes us take inflation more seriously. This is related to a question that Julius asks. Julius wants to know, if we use this model of the expanding muffin that I talked about in the book and in my talk for the cosmic background radiation, then where is the radiation located? Shouldn't we see the radiation all around us and not just at the fringes of the observable universe? You are exactly right, Julius. The radiation that comes from this plasma over here, the hot plasma 13.8 billion years ago, flies to us in the middle here where we see it now. So of course when we see the radiation, it's right here. A second before right the instant before we saw the radiation in our telescopes, it was very close to our telescope. It was on the way here. Everywhere else in space, there is also radiation going in all directions all the time. It's just that the radiation that reaches us now from far away, it was here 13.8 billion years ago. The whole part of space that we live in, all used to be super hot. So there was all this heat radiation flying in all directions all the time. And if someone goes, somewhere else and photographs the radiation that left here, this part of space where we live 13.8 billion years ago, that radiation would be what they call their cosmic microwave background. Then we have a question from Sukhjit, who, apologize if I mispronounced your name there, who wants to know, can the newly discovered subatomic particles at CERN give us any clues about dark matter? And the answer to that will depend a lot on what we actually discover. That so far, what's mainly been what the most recent thing we discovered, of course, was the Higgs boson, which does not necessarily have much of anything to do with dark matter. Rather, it explains why other particles have mass and so on. However, we're also very excited in physics about the possibility that the Large Hadron Collider, now when it turns on with more energy, might be able to discover other particles. maybe so-called supersymmetric particles. Maybe it can discover the lightest supersymmetric particle that exists, if there are any such things. Because that particle, if it exists, might actually be the dark matter particle. Or maybe there are even many kinds of dark matter particles, and what we can discover will be one or more of them. What do we know about dark matter so far? We basically only know what we've been able to weigh. We haven't seen dark matter because it's very shy, and it's transparent. Light just seems to go right through it. Dark matter also is shy in the sense that it doesn't interact with a so-called strong nuclear force. It doesn't get attached and stuck inside of atoms, which means that the molecules that in your body don't have like dark matter built into them. The only reason we know dark matter to be there so far is because we just feel its gravitational pull. You can discover anything that gravitates just from its gravity alone. For example, suppose the sun were totally invisible for some reason. We would still know that there's something there, because we would see, oh, Earth, our planet, is going around in a circle like this. That's weird. Planets are supposed to, just according to Newton's laws, go in straight lines if nothing is pulling on them. So the reason Earth is going in a circle like that once per year must be because there is something pulling on it with a gravitational pull, making it go in a circle. And we could figure out from the fact that it takes a year to go around, and the fact that it's 1.5 times 10 to the 11 meters in radius, the circle that we go in, that this thing must weigh about 2 times 10 to the 30 kilos. So we could weigh the sun even without seeing it. This is very much the situation with dark matter. Vera Rubin discovered that she could play this exact game I just described with weighing the sun to instead weigh the galaxy. So you look at stars now moving around and around the Milky Way galaxy, and you use that to figure out how much mass there must be there inside the orbit of the star. And what she found was there was way more stuff there, way more mass there than in the stars and the gas that you could see with your telescopes. That's the evidence we have now for dark matter. And it's kind of frustrating to be able to weigh stuff and say, oh, there's a substance, it's there, it forms clumps, this is how dense it is, and not know anything more about it. So what the hope is and this is, again, the core of your question, the hope at CERN is that maybe we can actually produce some dark matter particles of our own and learn the physical properties of them and see, and once we can do that, figure out if this is the kind of thing that our baby universe will also have produced in about the right abundance to be dark matter. So that's a very good shot on goal that we're getting now in terms of being able to make a break in the dark matter mystery. Another cool thing I'm excited about is catching dark matter particles. I told you that they're very shy. We don't see them. In fact, if a dark matter hits my hand, it'll go right through, it'll hit the Earth and probably go through Earth and go out. But once in a while they do bounce off of ordinary atomic nuclei, and there's a lot of different teams around the world who've built very cleverly designed detectors trying to catch dark matter as it flies through Earth. That's another shot on goal. I wouldn't be surprised at all if one of them announces within the next few years that yes, we have caught dark matter particles. Even cooler is, of course, if they catch them and the Large Hadron Collider produces them, and we can see that it's the same thing. Yet another third exciting possibility is to look for other weird evidence in space that we can interpret as dark matter. There's a lot of strange kinds of radiation coming to Earth that might be caused by, for example, 2 dark matter particles colliding with each other, annihilating and turning into some more ordinary kind of matter that we can see. And a fourth thing, which is also very cool, is to keep pushing the one attack on dark matter that's been so successful, namely weighing it, and do it better by looking in much more detail at how all this stuff is moving around in our universe with various kinds of telescopes, we can start making much more detailed maps about where the dark matter is, how it's distributed, and from that also learn more about the nature of dark matter. Then we have an interesting question here from Donna, who asks, do you believe there could be intelligent life on other planets in our universe? Why or why not? So could there be? Of course there could be. I think you'll be very arrogant to presume that there's some kind of law of nature saying that quarks and electrons can only arrange themselves into self-aware beings here on Earth and nowhere else. But could is not the same. That it could happen isn't the same as saying that it actually has happened. Right? This is very much a matter of probabilities. What's the probability that a typical solar system will have at least one planet where life will evolve, that will then become intelligent enough to build telescopes and start asking these kind of questions? We don't know. We know for sure that the probability isn't zero because it happened here and we're having this conversation, right? But we also don't know that the probability is large, right? It could be that somehow it requires a wild stroke of luck so that our nearest neighbor civilization might be very, very far away. And what you're specifically asking is exactly the right question. Do I think that there's other intelligent planets in our universe, right? You're not asking, do I think that there is intelligent life anywhere in an infinite space, say? You're asking, is there intelligent life in our universe, in here? That's the really interesting question to me. Because if there is intelligent life somewhere in this region of space, the region of space that we can in principle communicate with and access, then it's actually relevant to us. We can actually interact with these other life forms. And so what do I think? This is a pretty big space, right? There are hundreds of billions of stars in our galaxy. Many of them have planets. There are also hundreds of billions of galaxies in here. There's altogether 10 to the power 78 protons. There's a lot of stuff in here. So how far away is our nearest neighbor, if there is one? Is it way outside this or way inside? We really don't know. Most people I talk with who are not scientists or who haven't thought about this so much will say, well, of course there's intelligent life there out there because there's so many stars, right? But the interesting question is how far do you have to go to find your nearest neighbor? The scientific rigorous answer is we right now have no clue if the probability of getting life on a given planet is 10 to the minus 10 or 10 to the minus 20 or 10 to the minus 30 or 10 to the minus 40 or 10 to the minus 50, 10 to the minus 60. We really don't know. It might be that before we looked with telescopes and learned anything from actual observation, you might have thought, well, it's very likely, it's pretty much automatic, the universe evolves more and more complex things, and then there's like a natural evolutionary drive towards more intelligence, so it's close to 100%. We now know that's totally false. We have not seen, we've seen a lot of other planets, a lot of other solar systems with no indication whatsoever of there being civilizations there transmitting things we can detect. Our galaxy itself has many planets which are probably quite Earth-like. They're 2 billion years older than this one. Right? If you have a civilization at the level of ours and we don't do something stupid like annihilate ourselves and we instead spend millions of years perfecting our technology, it's pretty easy to colonize the galaxy. We could easily do it in millions of years, let alone billions. Which led Enrico Fermi, the famous physicist, to say, hey, where are they, all these aliens? If most planets out there that are Earth-like develop advanced life that then goes on and colonizes space, at least a bunch of them should have colonized us long ago. Yeah, sure. Maybe some of them prefer sitting around meditating and you know in doing things which don't involve colonizing space. But all it takes is one civilization out of the whole bunch that thinks it's cool to colonize, and we would have heard from them. So it's not super common. We can say that. There are also a lot of things that we've discovered now in our own history, which suggests that it wasn't such an automatic journey from non-animate dead things to telescope building, internet surfing life. We don't know for sure whether there were some complicated coincidences required in the beginning to get the very low-level self-reproducing organisms going. For example, my proteins in my body are assembled by this complicated machine called the ribosome, which reads the DNA and builds stuff. Well, but to build a ribosome, you need a ribosome, and maybe this could have evolved in a sequence of many, many small steps. So it's very likely maybe it required actually a lot of luck. So you need to have a huge number of planets out there for it to happen on one of them. We just don't know. Look at another example is higher intelligence. So look at the dinosaurs. They were stomping around here on Earth for over 100 million years without inventing even the internet. So I think it's pretty clear that we can't take for granted that, whenever you get something as smart as a snail or a squirrel or whatever, it's automatically going to soon become as capable and intelligent as we humans. We just don't know. So I do a little bit more quantitative argument about this in the book, and say if it's basically equally likely that the probability is 10 to the minus 10, 10 to the minus 20, 10 to the minus 30, 10 to the minus 40, etc., that you get life on one planet, that translates into saying that the distance to our nearest neighbor is equally likely to be 10 to the 10 meters, 10 to the 20 meters, 10 to the 30 meters. But wait a minute, it can't be much less than 10 to the 22 meters, because then it would have been in our galaxy and the Fermi paradox, and we should have seen them already. And if it's more than 10 to 26 meters, well, we're already outside of here. So my own guess, and this is a very controversial and contrarian guess, you should be warned that most people do not guess this way, but I guess this, is that we are actually the only life in this entire observable universe that has gotten as far as building telescopes. We don't know that for sure, but to me, the fact that it's even a possibility means we should be we should take very, very good care of our planet and not be reckless with it. We should not say, it doesn't matter if we screw up our environment and go extinct or something, because there's all this other life there anyway, all around our galaxy and our universe, and life will be fine without us. We should not be reckless. Think that way. Instead, what we need to say is, look, there's a real possibility that we're alone here, which makes us incredibly significant. If you think the galaxies are beautiful, they're beautiful. Why? Because you, as a human, with your telescope, can look at the galaxy and be consciously aware of it. That's why it's beautiful. And in this picture, if we're the only ones here, we shouldn't look for our universe to give meaning to us. It's us who give meaning to our universe. And if we do something really dumb, which we've been on the verge of doing for some time now on our planet, and go extinct, then our whole universe becomes meaningless. It just becomes a giant waste of space. Nobody's aware of it. I think that would be a terrible shame. So your question actually leads me to feel very strongly that we humans need to think more long-term. That we have incredible opportunities. We live in this vast universe with all this awesome opportunity. The same technologies that we're inventing now that can wipe us out can, of course, also help life flourish to new levels not just here on Earth, but throughout our universe, maybe one day in the future. And let's work together and try to really seize that opportunity, rather than just assume life is so common that we like to say it's I don't worry, and wipe out. Let's make a difference. Then, let me just take a deep breath and turn to a question from Colleen, who asks, if dark matter interacts with gravity, is it possible that there might be some dark matter at the center of Earth? And what about in black holes? The last question I gave a very long answer to. This one I can give a very short answer to. Yes, absolutely. For the black holes. Dark matter, if it falls into a black hole, gets eaten, just like any other stuff, and won't come out. So the black holes that are out there have undoubtedly gobbled up, their share of dark matter. As to Earth, the main question is whether you can slow down the dark matter particles enough that they would stay in the center of Earth. If I take some dark matter, if I take my phone and I throw it upwards slowly, it'll just fall back down again. But if I throw it upwards faster than 11.2 kilometers per second, the so-called escape velocity from Earth, it will never come back. Just leave. Similarly, if a dark matter particle comes flying down from space at a very high speed, faster than 11.2 kilometers per second, by the time it's gone through Earth, it's just going to leave Earth again and not stay here. And the typical dark matter particles whizzing around our galaxy, we think are moving at hundreds, maybe a couple hundred kilometers per second. It's like 20 times as fast as the escape velocity from Earth. So most of them, when they hit Earth, they just go right through like a bullet and out on the other side. To trap a dark matter particle here, you would need to get it slowed down somehow. It's kind of hard. But there has been some interesting work, for example, by the astrophysicist Georg Raffelt in Munich, who looked at if maybe stars can be better at catching dark matter particles. Because they're so dense and so thick that there's more of a chance that the dark matter particle might not actually bounce on some stuff, and you might start building up a little cloud of dark matter at the center of stars. And this is actually one cool way you can put bounds on what kind of things, what kind of properties dark matter might have. Then we have a question from Sergey, who asks, suppose we could derive some math equations to calculate everything. Our thoughts, behaviors, fates. What do you think would be the consequences of this knowledge? So that's a really fun question. In particular, since I'm an optimist and I actually think that we can in principle derive some math equations to calculate, to understand everything there is to understand about our world. And that is, again, the most crazy and radical idea that I explore in this book. That's why the word mathematical is in it, right? So what would be the consequences if we succeed of this? Well, first of all, you might say it should change the way we view ourselves a little bit if everything is ultimately mathematical. I don't think it would actually change very much the way we live our lives, the way we feel about our loved ones, and so on, because that's quite independent of what we know about our makeup. After all, do you really think that people enjoy chocolate less now that they know that chocolate is made of molecules that are made of carbon atoms and oxygen atoms and hydrogen atoms? It still tastes exactly equally delicious, and when you're enjoying that chocolate, the experience you have is quite independent of the substrate of the chocolate, whether it's made of atoms or whatever. And if you then learn that those atoms are ultimately completely mathematical, I don't think it's going to change either your chocolate eating experience or for that matter, how you feel about your loved ones or much else. However, I do think if it's true that everything can be described by math, I think, to me, that's a very optimistic and happy outcome. In that, if you think about why is it really that we humans have been able to figure out so much about the world, through science. Why is that? Why have we been able to invent all this technology that lets us have live stream webcasts here and go to travel into space and so on? I think the key reason why we've succeeded in this is because nature has been so kind to us and given us all these mathematical clues. It started out with just a few clues, like Isaac Newton discovering that, hey, there are these simple equations that describe the motions of stuff. And gradually, more and more clues turned up that describe not just how things move, but also why things have the colors they do and the material properties they do. And Schrödinger, for example, when he discovered the Schrödinger equations, gave us the master key to understand all the properties of atoms. Using them, we can calculate why my fingernails are hard, but my flesh in my hands are soft, and why it has the color it does. All of this stuff. So gradually, these mathematical equations we've discovered have given us more and more insight and power. And if it's all mathematical, then the fact that we still have a lot of things we're clueless about and don't understand means, of course, that there's a lot more of these clues out there that we haven't yet found and that we will find if we look hard enough, or at least that we have the opportunity to find. And to me, that's very exciting. There's no guarantee, of course, that the clues are there or that we can find them. But the best way to fail in any endeavor in life is to tell yourself, this is impossible, and therefore not even try. I feel that if we humans should fail, we should at least go down swinging. We should act as if there is a possibility of finding these clues, and let's team up and look real hard for them. And hopefully we'll find even more of these great mathematical clues and be able to understand and further improve our world. Shifting gears a little bit, we have a question from Javier, who asks, if there are galaxies receding from us faster than the speed of light, are they beyond the cosmic microwave background? Isn't the cosmic microwave background, in other words, isn't this stuff that you see at the edge of our observable universe, isn't that the furthest place that we can see? So the answer is yes. The microwave background is indeed the furthest place, the stuff that we can see. Stuff much farther away from here, light from there would not yet have had time to reach us. What about galaxies that are receding from us much faster than the speed of light right now? Yes, they are in fact farther away than this. That's why we can't see them yet, because light from them just hasn't had time to get to us. Just one thing I want to clarify, and this might be the crux of what intrigued you about this, is we are seeing this hot plasma that gives rise to the cosmic microwave background. We are seeing it the way it was 13.8 billion years ago, of course. But right now, in this part of space, things have cooled off, and the gas is clumped together into galaxies, stars, and planets. So right now, there are galaxies there. But to see them, we would have to wait even longer for the light from there to reach us. So when you talk about galaxies flying away from us now, farther away here, faster than the speed of light, it would take even longer. If suppose you go another billion light years away from this, you might think you only have to wait a billion years to see light from here. You'd have to wait much longer, because first you have to wait for the first light to reach us from there, back from when this was super hot plasma. And then you have to wait billions of years until you see that plasma gradually turning into galaxies that shine at us. Then we have a question from Sem, who wants to know, how close are we to finding the answer to the question, where do we all come from? So the cool thing about this question is it's really a set of nested questions. There's always been a frontier of our knowledge in the past, right? Throughout human history, people have always known where they were this morning, what they had for breakfast. But back when people lived in caves, they had no clue where the caves came from, where Earth came from, how planets were formed, what. Now we've pushed the frontier of knowledge backward in time. First of all, back in the days of Newton already, they were able to figure out where our planet was, where the other planets were hundreds of years ago by solving the equations of motion. And then we were able to figure out as a community that the planets actually themselves, where they came from, that they came from gas clouds that were clumped together by gravity and formed solar systems, stars with planets spinning around. But then you can say, okay, where did those gas clouds come from? Well, now we know that all of those gas clouds came from this hot, expanding plasma that was here 13.8 billion years ago. It was very uniform and boring, actually, much like the air here in this room, but with tiny, tiny fluctuations in the density. So maybe it was 1,000% denser here, 1,000% less dense there. Much like it is right now, actually, the air, because I'm talking. There were also sound waves in our early universe. And then gravity amplified that, causing these clumps to get bigger, to turn into bigger clumps, those gas clouds, which then form the stars and the planets. So that's progress. Now we push the frontier of our knowledge back from today, 13.8 billion years in, back to the first second or so. But then where did that hot plasma come from? That we don't know. Although there's been very nice progress there also, as I talked about in the inflation lecture here, and the whole chapter 5 of my book. We have a very compelling story in the inflation theory for this, that says that if you just start, maybe all of that came from a tiny speck of stuff, way smaller than an atom, with less mass in it than an apple, and which, because of this inflation process, just kept doubling over and over again until it had produced more plasma than we needed to make all the galaxies in our observed universe. We don't know yet whether that's true or not, but as you know, there's very active work on it and all this exciting controversy about the bicep observations, which we should find out more about within the next week, actually. There should be a new cool paper out telling us more about how seriously we should take this. And but that still doesn't fully answer your question, Sam. Where does everything come from? Because you can still ask, okay, if everything came from this tiny speck of hard to dilute stuff, well, where did that speck come from? How did inflation get started? And this is something which is on very shaky grounds right now. Part of the reason for that is we might need a theory of quantum gravity to even ask the question properly. We don't have one because we've embarrassingly failed to unify the quantum theory of the very small, which you obviously need to describe a small speck, with the gravitational theory of the very heavy, which you also obviously need to describe that thing. So that's the current frontier of ignorance. And let's keep pushing it. Finally, we have a question from Al, and that's the last question. And it's perfect timing since we're coming up on the hour. Al asks, if our universe is indeed infinite in space and time, wouldn't our universe be expanding into the pre-existing gravitational field that would eventually cause the expansion to speed up? In other words, is dark energy just gravity from the larger universe? Dark energy is a very pesky mystery. We would like to know what dark energy is because it makes up, about 70% of all the stuff in our universe. We currently have no clue what it is. We unfortunately can't explain dark energy quite this easily, because whatever gravity is doing outside of our universe, whatever is going on out here and here and here and here and so on, right now is having no effect on us at all, because the effects of gravity only travel at the speed of light. So if there's something that light hasn't had time to reach us from, then its gravitational effects haven't had time to reach us from there either. And dark energy is already having an effect on us. So dark energy seems to be some kind of stuff which is very hard to dilute. It seems to be, as far as we can tell, completely constant everywhere in space to have this substance, and it seems to have the same density everywhere in space, and also at all the different times that we've looked. And doesn't this sound vaguely familiar, strangely familiar? Actually, weren't we just talking about such a substance? Yes, we were. Inflation postulated also that there was exactly such a substance, right? In the very early universe, something which is very hard to dilute, causing things to expand in an accelerated way. So, in fact, dark energy seems to be inflation starting over again, just in slow motion, doubling its size, not every hundredth of a trillionth of a trillionth of a trillionth of a second, but maybe once every 7 billion years or so. And I'm hoping that we'll find that one day these two phenomena are kind of linked, so that if we can learn more about inflation, it will shed more light on dark matter, and vice versa. Let me take a quick look here before we declare victory and part ways here, to see if any more questions have come in by email. And I have a message here from the World Science U team, from Julian, saying, more questions for you are coming in. I will try to keep replying to this thread. Let's see here. Refresh my inbox. I don't see any more questions quite yet. Let me click refresh one more time and see if there is anything here. Yes, we have a question from Chris, who wants to know, what do you expect from the new Planck data next week? And which next observational challenge is your favorite? So that's a very cool question. We've had a lot of fun today looking at our universe, this iconic image of it from the WMAP satellite. We have an even sharper image now from the Planck satellite. And what's particularly exciting is that now, hopefully next week, we will get Planck's first ever pictures of what this looks like in polarized light. Crudely speaking, imagine looking at this stuff with polarized sunglasses. This is super interesting because the smoking gun signature of this inflation theory that we talked about are a certain kind of distortion of these patterns that you can see most clearly in polarized light. And as most of you heard, there was a huge splash in March when the BICEP 2 experiment announced that after 3 years of very hard work at the South Pole, they had found the Holy Grail, this signal of the smoking gun signature of inflation in their maps. Then this got marred in controversy, and it started to become clear that actually at least some of what they had seen was not from the baby universe. It was contamination, microwaves coming from dust emission in our own galaxy. So the million-dollar question is, had BICEP only seen dust, or had they seen some dust and also some of this smoking gun signature inflation? It'll be very exciting next week to get more light shed on this. The Planck satellite has teamed up with the BICEP team, and they've taken the BICEP maps and put them on top of the Planck team maps to see if the features line up. In particular, if the dust features that the Planck satellite has seen at higher frequencies line up with these sensational features that the BICEP team saw at lower frequencies. And I, for one, am going to jump on this paper as soon as it gets posted on the archive and be very excited to see what happens. If it turns out that the results are inconclusive and they can't say one way or the other whether it's all dust or whether it's both dust and the sensational proof of inflation, Then there's more good news to look forward in 2015. John Kovac from the BICEP 2 experiment told me that that's when their new results from the Keck array should hit the internet. What they've done is they've spent also years looking at the same part of the sky with a different frequency, closer to 100 gigahertz instead of 150. If you look at a signal from the sky and you want to figure out what is this the cosmic microwave background baby pictures of our universe, or is it dust? There's a very easy way to do it. You look at many different frequencies and compare them. You basically look at the color of the light, because the cosmic microwave background has a very special color. That corresponds to what we call black body radiation at about 2.7 degrees over absolute zero. Whereas dust has a much more bluish color. There's more high frequency relative to low frequency. And that data should really help nail it if the Planck data next week does not. And let's see if there are any more questions here. Michael asks, are we any closer today to understanding the shape of the observable universe? And if so, what are the possibilities? Is it bounded or unbounded? So, for Michael's question, the observable universe is simply this, which is by definition a sphere, the part of space that we can see. But that's not very profound. It's just like saying, if you go out in the fog again and the visibility is 100 meters, the region of space you can see is a sphere. That doesn't tell you very much about the nature of reality. It just tells you that, well, if you look at all points that are 100 meters away from you, they form a sphere. The really exciting question, which is I think is what Michael is really getting at here, is what's the shape of space? What properties does space itself have? For example, is space curved or not, and does space go on forever or not? When I was a kid, I thought, of course space has to go on forever. I mean, how could it not go on forever? Would there be like this a sign saying, warning, space ends here, mind the gap, as I talked about in the lecture? And if so, what would be on the other side? That would seem pretty dumb, right? But Einstein gave us a much more elegant way in which space could not be infinite. He said maybe space is curved, like the surface of a hypersphere or something. So you just go really, really far in one direction and you find yourself coming back from the other. Well, the cool thing is, if space is curved, then the geometry of it is different. If you draw a triangle on my blackboard at MIT, its triangles add up to 180 degrees. If I draw a triangle on an orange, the angles add up to more than 180. And in the same way, we've actually looked at, me and many other cosmologists have looked very carefully at the biggest triangles you can imagine in this part of space, going from us in the middle to the edge of our universe, across to the side, to the other side of one of these little blobs, and then back, and checked what the angles actually add up to see whether space actually seems curved or not. Basically, to see whether what it boils down to is looking at these, if the typical size of these red and blue spots here are about the angular size of the moon, like half a degree, or whether they look bigger or smaller. And what we've been able to measure with about 1% accuracy is that they're exactly the size they should be if space is flat and infinite. So there's not a shred of evidence yet that space is not infinite. Moreover, there's actually a very interesting prediction from inflation about this, because inflation says generically that space is not, it's going to make space, really, really big space, it's going to make a space which is not just huge, but actually generically even infinite. So if any of these kinds of inflation models are true, then the answer to your question, Michael, is that that space might very well be unbounded. And the cool thing is that the more we learn about inflation, right, the more light gets shed on your most excellent question. So with that, I have reached the end of all of the awesome questions that you sent me. Thank you so much for tuning in. Thank you so much for all the great questions. one of the coolest things I find about being a scientist is I get to think about fun questions like this all day long, and it's so much fun. I would happily do it, think about these questions just as a hobby, and then I can even get paid for it and call it a job. It's like the ultimate scam, you know. So in particular, if you're young and still trying to figure out what sort of career you want to do, and if becoming a scientist is something you're considering, let me make a little plug for it. Being a scientist is just so amazingly cool. I can't think of any job in our universe that I would trade my job for. And I feel very, very fortunate. Basically, I feel that being a scientist is like getting to be part of this most amazing detective mystery of all time, trying to understand the mystery of our universe. And you actually get to be one of the detectives and look at the evidence and try to figure stuff out. And even though a lot of the questions are hard, I think it's just astonishing how much we humans have been able to figure out, even in the last 10, 15 years. When I was a grad student, we argued about whether our universe was 10 billion years old or 20 billion years old. And now we argue about whether it's 13.7 billion or 13.8 billion years old. So that's progress. Thank you, everybody.